Okay guys, so welcome back. So this is going to be our first video about the Bayesian networks. And we'll have a long series of videos now because we'll start in discussing what are Bayesian networks and how we make one. And we will discuss the graph and also the parameterization. And we'll move after those videos to other videos where we look at several different applications. So we're going to see some use case of Bayesian networks and how it's used. So it's more focused on modeling and what kind of answer we can get from those models in different problems. So let's get started. So in this first video, we're going to start discussing Bayesian networks, and we'll focus a little bit on the graphical structure, independencies, and the parameterization. So we're going to start with the basic understanding of Bayesian networks. Our motivation is that idea that we cannot represent the joint distribution because it's exponential in size, considered the number of variables. So we needed to find a more compact representation. If we try to model the joint distribution, we'll have a huge table. It will be very difficult to get the probabilities because if we ask those probabilities to a person, it will be very difficult for that person to know that because the probability will be very small, and each event will be a composition of several different conditions, so several different values for the variables. So it will be very difficult to do. If you will say no, we're gonna do the machine learning way and we will get those probabilities from data, it's still very difficult because the table is exponential in the size, in the number of variables, so you're going to have an exponential size, and we still have to find at least, I don't know, a basic rule of thumb for this is to have at least 10 data points for each possible probability, so for each possible assignment. So imagine you need a huge amount of data in order to get some accurate estimates for the distributions. So it'd be very hard to work with that. The algorithms working in that representation would be exponential in time. So we needed to find a factorized representation for the joint distribution. Another thing is that when we work with the joint distribution, it's very difficult to have any insights about that. It's going to be a huge table full of numbers. So for instance, to understand what are the independencies there, it's very difficult just looking at the numbers. I included in the tutorial one exercise where I give you a small joint distribution and ask you what are the independencies there. And in order to answer that questions, we need to factorize and change the representation because looking at the joint distributions is difficult to say which variables are independent, which ones are conditionally independent of others. So this representation using graphs will make the independence between variables very clear to us. So Bayesian networks will be our first graphical model. It is a directed cyclic graph that we call a DAG. It will compose it by nodes and edges. The edges have direction and there are no directed cycles. So we'll think about the edges as representing a directed causation, so a directed causal influence. I have an example here, and it involves a series of variables. So each variable will be associated to a node in the graph. So we have earthquake here is the variable E, burglary, radio, alarm, and the call. And in this graph, what we are saying is that an earthquake can make us hear a report on radio talking about the earthquake. So if we have an earthquake, it increases the chances of having a report on radio about that earthquake. The earthquake is also a possible cause for an alarm. So we know that our alarm can be triggered by an earthquake as well as a burglary. So the burglary is a second cause for the alarm. And if we will have the alarm triggered, a neighbor can call us and say, you know, I noticed that your alarm is triggered. Are you at home? Do you want me to check that? And so on. So this is the basic idea of this graph. And the edges are direct causations, but it doesn't mean that one variable that's not directly connected through an edge to another variable is not influencing that variable. There is a chain of influence that's passing through the nodes, and one node that's distant from the other still can influence that node. So for instance, if we take here radio, right? If we listen to a report on the radio about an earthquake, that will increase the chance that we had an earthquake in the area that we live. That will increase the chance of the alarm being triggered by the earthquake, and that increase the chance of having a call from a neighbor. However, that influence might be blocked by the variable if we observe the variable. So let's suppose that we know that there was no alarm. So for instance, we are at home, so we know there is no alarm. The alarm was not triggered. It doesn't matter if we listen to a report on radio about an earthquake. It doesn't matter if we had an earthquake or not. That earthquake was not strong enough to trigger the alarm. It doesn't matter if we had a burglar or not. The burglar did not make the alarm to trigger for some reason. So the chance of having a call from a neighbor will be the same, because the alarm was not triggered, and the neighbor is likely not to call us. So we say that C, that is the call variable here on the bottom, is independent of R if you know that there is no alarm. So if the alarm was not triggered. So it would be good to introduce a little bit of notation so we can make our definitions clearer. So we will define parents, descendants, and non-descendants of a variable. Let's use A as an example here. So A has two parents, that's E and B. So we know that because there is a directed edge from the parents to A. A has only one descendant, that is C. But it also would include as descendants of A any other node that we have here, that we have a path from A to that node. So if you had a node here like a D, that would be included in the descendants of A. And we have the non-descendants. In the case of A, the only non-descendant is R. So the non-descendants are the nodes that are not parents or descendants. So parents are E and B, descendant is C, and non-descendant is R. So a graph like this one is representing a series of independence statements. And the independence statements have this form here. The variable is independent of the non-descendants given the parents. So we are saying here that A is independent of R given the parents that are E and B. And we know that is not the only independence statement that we have. We can do also other statements similar to this one to the other variables. And we call this set of independent statements as the Markovian, there's a typo here, this is the Markovian assumptions of G, of the graph G, and we denote that by Markov G. So basically what we are saying is that every variable is conditionally independent of its non-descendants given its parents. If we view this graph as a causal structure, you are understanding that the parents of a variable are the direct causes and the descendants are the effects of that variable. So in the case of A, we have E and B as direct causes, and we have C as a possible effect. And what the Markovian assumptions are telling us is that if we know, if it's given the direct causes of a variable, so our beliefs in that variable will no longer be influenced by any other variable except its effect, right? So it's saying that if we know if an earthquake happened or not, if we know if a burglary happened or not, that will be enough to determine our beliefs in the alarm. Those beliefs can be influenced by a neighbor calling us, but will not be influenced by listening to a report in the radio. All right, we will see a little bit more of this, why it's true and what is going on as we understand the parameterization of a Bayesian network. But let's, for now, state all the Markovian assumptions that we have in this graph, just a sort of an exercise. So let's look at the R variable first. So it's saying that R is independent of all non-descendants. So R have no descendants. It has a parent earthquake. It's the only parent. So burglary is not a descendant, and it's also not a parent. And that also happens to A and C, given its parent. So R is independent of all non-descendants, given its parent. Let's look at E, right? So E has no parent. Okay, so E is going to be independent of all non-descendants. Okay, the descendants are R, A, and C. So the only non-descendant is B, given its parents, but E has no parent, so there is not included here. B is independent. So the descendants are A and C. So we have two non-descendants, E and R. Given its parent, there's no parent, so there is nothing to include here, or we can include an empty set if you want to, but it's not necessary. Okay, we have A independent of R, given its parents, E and B. And finally, we have C is independent of all non-descendants. So the non-descendants are E and B, given its only parent, A. So this all the Markovian assumptions in this. Okay, but that's not all. We are represented with the graph a set of independencies, but there will be many possibilities of different distributions that we can represent with that set of independencies. So we have to complement this graph structure with a series of probability tables, and we will have one conditional probability table for each node. So when we make this representation, that is the graph together with the probability tables, we will have a unique definition. So there will be only one probability distribution that will be represented by this composition of graph and tables. And that is very interesting. Actually, this representation is not only unique, but it's complete, and it has a very clear meaning. It says that if we look at a joint distribution, there will be one probability that's specified for each possible entry of this joint distribution. So we will have all probabilities specified. There will be no situation that we have one assignment that has no probability assigned to it, so it will be complete. At the same time that each probability, so it will be complete, and each probability will be unique. It means that if you ask the question several times about that probability, the results are always the same. So that are very important and very useful properties of the Bayesian network. So we usually work with causality. So this idea that we include an edge to two nodes in the direction of the node that is causing and the node that is being influenced. So the edge comes from the node that is generating the influence to the node that is being influenced. And this interpretation makes the graphs easier to understand. And if you are working with domain experts, it's going to be easier also to elicit the probabilities. So, but it's very important to say that the definition of Bayesian networks does not mention anything related to causality. So the causality is sort of a tool for modeling the Bayesian network. But it's totally possible to build the Bayesian network and one of those DAGs not using causation at all. And there is one example here in this slide. So these two Bayesian networks, the first one was built using the idea of causation, and the second one, it wasn't. And it is strange to accept this, but both networks have exactly the same independence statements. So they are assuming the same conditional independencies between the variables. It's clear that the first one is easier to understand than the second one. But as we will see in a few slides, when we introduce the concept of independence maps, we will see that both networks have the same independence map. Great, so the second part of the Bayesian network specification is the parametrization. So now we're going to quantify the strength of the causation between the variables, or the strength of the dependence between the variables. So the parameterization is very simple. It's basically one conditional probability table per node. And this conditional probability table will include the variable in the node conditioned to its parent. So if we look here on the top, we have this variable winter. That's the variable A, and this is the conditional probability table for this variable. As it has no parents, there is no conditioning variable, so it will be a prior. So we have the probability of A and not A. So A is winter, so there is a probability of being in winter or not being in winter. If you look at sprinkler, that is our second variable here, it has this conditional probability table. As A is parent of B, we will specify the probability of B given A. So we have here two situations where A is true and Y is false. So we have winters and not winters, and we have the sprinkler going on or not in these two conditions, like winter, we have winter and not winter. So we can say, for instance, that it is winter, the probability of having the sprinkler being activated is smaller. If it's not winter, it should be hotter, and we need to activate the sprinkler more often. The same thing for variable C. So C is rain, and we have its conditional probability is specified in here. So C has A as a parent, and is the probability of rain. So we have here winters. So in the winter, the probability of raining is higher than not raining, and when it's not winter, we have a higher probability of not raining. And this is the conditional probability for E, and this is the conditional probability for the variable D. So as D has two parents, it will be a larger table. It will involve three variables, B, C, and D, and will be specifying the probability of D given BC. So the probability of variable D given its parents, there are B and C. So we see that, well, if we have 1, 2, 3, 4, 5 nodes, we will need also 5 conditional probability tables. It's interesting to see that if we sum the values of x, keeping the parent constant, it will sum to 1. So we can understand each conditional probability distribution as a set of family of distributions. Remember that in order to have a distribution, the probabilities must sum to 1, right? But when we look here, the probabilities do not sum to 1. Actually, this one sums to 2, this one is summed to 1, 2, 3, 4, this sums to 4, this sums to 2, and this one sums to 2. And this is the only one that is a probability distribution because it's not conditioned to anything, so it sums to 1. Right? So what is the reason for this strange behavior is the fact that when we are conditioning to something, we will have a distribution for the variable for each possible instantiation of the conditioning variables, right? So here we have a distribution for b given that a is true, so this will sum to 1. And here we have a distribution for b when a is false. So that is the idea of the conditional probability. If a given b, I will have a distribution for a for each possible value of b that is conditioning. So if b occurs, like if a variable b is a binary variable, if b is true, so yeah, we're going to define the distribution for a. If b is false, we have another distribution for a. And that happens here too. If you think that we have one distribution for d for each possible value, each possible assignment for b and c. So here we have b and c being true, we have a distribution for d. Here we have b and not c, and we have a distribution for d. If we have not b and c, and another distribution for d, and here we have not b and not c, and another distribution for d. That is a property that we frequently use when we are doing some analysis or some proofs. Sometimes we get into an expression like this that we needed to sum for a value of one variable conditional to something that's fixed, and we know that is going to be 1. It's useful sometimes in some proofs. That's important to remember that. Another thing that's important here is because as this condition probability is sum to 1 for each possible assignment of the conditioning part, we need only 11 probabilities in order to specify this complete network. So we have 1 here because they sum to 1. I only needed to specify, for instance, the top one. The second one here, I can derive from the first one because we know that they must sum to 1. So it's going to be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, plus 1 here, 11. So we need 11 parameters. As we have 5 variables here, if we specify the joint distribution, it will be 32. So it's 32 against 11. So it seems that we're gonna save in some space by doing this factorization. Of course, that's not very clear because we are working with a small number of variables. But this difference tends to increase as we increase the number of variables too. Okay, that's a good start for Bayesian networks. Let's have a break, stretch a little bit, have a coffee, and we will continue with the discussion about Bayesian networks and dependencies. See you soon.